thank you for coming back. Should we do counts? No, let's not do counts. Exactly, we're back for part 2, and yeah, kind of what I hinted at in this morning chapter was that we were talking about this like thing called Bayes' theorem that allows us to go from prior to posterior after we receive data. Then we talk about well-posedness of Bayes inverse problems, because that's kind of what I know about a lot. And what I kind of hinted on before was that inverse problems usually are actually ill-posed. So there could be multiple solutions, there could be no solutions, or solutions could be kind of unstable in the data, which is annoying. And I will try to persuade you that Bayesian inverse problems are almost always well-posed. So it's actually not trivial to give an ill-posed example for Bayesian inverse problems. And then I will talk a bit about Bayesian point estimator. So kind of that's what you asked earlier. It's like, okay, but what actually is the estimator now? And I will kind of give you 2 examples. And one is very similar to classical regularization theory. We kind of see that it's not so different. The Bayesian theory is regularization theory. And one that is maybe more Bayesian, maybe more like what the decisions would use in such problems. Okay, but first, so I'm not one of the people that puts like comics on slides or memes on slides, but this one is kind of good. Can you read it?
Yeah.
Oh, we should get inside. Oh, it's okay. Lightning only kills about 45 Americans a year, so the chance of dying are only 1 in 7 million. Yeah, but if you know the statistics and you run outside, then chance is 1 in 4. It's like 1 in 6. So I guess that's conditional probability. All right, and then just kind of a small recap slide. So we were studying inverse problems of this form. So we said we're looking for some f star, and A is some operator, E is some noise, G is some data. And exactly, we try to figure out f star given G and given A, and okay, maybe having some idea of what E is. Then we said, okay, we model f star and we model E as random variables. So having a prior and a noise distribution. And those are not really, the model is random variables, but we don't really see them as random objects, although the noise maybe could be random technically, but we see them as a way to model reasonable expectation or uncertainty in the parameters. So it's not actually random. We don't actually believe that they are random. We just believe that we are uncertain about them, and that's how we model them. And then the basic idea essentially is to now say, okay, let's learn what we've learned about the parameter at start that we're looking for by constructing this posterior distribution. So that is essentially prior, but then conditioned on the events that we have seen the data. And then we have seen that, okay, actually conditional distributions are kind of complicated objects, so we kind of didn't really like, I really like them, but I think you didn't really like them. But conditional densities are much easier. So if we assume that the prior is a density, and then we can kind of figure out a posterior density potentially, and that makes it much easier to work with rather than working with the distributions themselves that are just given kind of implicitly through these Nicodemus formulas or equations. And then we actually said, okay, we generalize the problem a bit, so we actually said that, okay, rather than like this thing here, we just call this thing like big G, and we allowed it to be a bit more general. So that's just some random object that is obviously somewhat interlinked with f. If it's not, then it's a very simple problem, because then we don't learn anything. But so we think that there's some dependency between f and g, and this is one way the dependency could look like, but it's not the only way. So it could look quite different as well. All right. So that's a recap at the beginning of the TV show. Now, so we're back up to speed now, and have finished our soup coma. So that's what we have already. Okay. Now the question is, how do we get from prior to posterior? And as I just said, I hinted on using Bayes' theorem. And what Bayes' theorem actually really is, it's an inversion formula. In a way, because actually it doesn't really tell us how to get from prior to posterior. It actually tells us how to get from one conditional probability density to the opposite one. So if we know what the conditional density of G given the parameter is, so the data given the parameter is, we can use Bayes' theorem to get to the other one. which is the one we're actually interested in. So this one is the posterior density. So that is the parameter given the data. But Bayes' theorem allows us to get this from the density of the data given the parameter. Now I can say, okay, does that make anything easier? And actually it does, because this density of the data given the parameter is a very well-known object in statistics. It's called the likelihood, or the likelihood function. Okay, so that's something that we are often able to actually derive. And what it does is essentially it describes how well the parameter f describes the data. So kind of so like how likely is it that a certain data set is chosen given that f is the parameter. Okay, is that? Okay, this is wrong here. Okay, so this should be how likely is the data G if the chosen parameter is f. So f and G are flipped. I will fix it later. And actually, so if everything is well specified, which in inverse problems usually it's not, then actually we would assume that G is actually a sample from the likelihood is a density, so you can sample from that, is actually a sample from the likelihood given the true parameter. Okay, so that's like a well-specified problem, that's what we often assume, but then if there's like a PDE or so, then you need to find elements or something, then it's not quite true anymore. So you may have a misspecified problem, but if it's well-specified, then this will actually be true. Yes? Then G is just a sample from this, given the true parameter. Okay. So in our particular Bayesian inverse problem setting that we like, so the one with the additive noise, it's quite easy to get this likelihood, because likelihood essentially is determined by this like structure here, so by the additivity here, and by the noise distribution kind of over there. Because what this essentially says is that like G, depending on f, is just a Gaussian sample, with the mean given by like A of f. Okay, that's just written down here. The likelihood of f, bless you. Okay. The likelihood of f given G is just given by this Gaussian-ish density. Okay, so it's a Gaussian density in G. It's not for an f, obviously, but it is a Gaussian density in G conditional on we know f. Okay, and so to see that, you can just kind of subtract G and put E on the other side, or kind of subtract A if you want to. So then you see like if like E is equal to G minus A of f, and then it sort of says like, okay, so like G minus A of f needs to be Gaussian distributed because E has a Gaussian distribution, and then you see quite quickly that's okay, this has to be the correct likelihood. But as I said before, there are also settings that have very different noise models, and then you would get a very different likelihoods. So if the noise is multiplicative for some reason, then this would look like very differently potentially. Okay. Now if we have this likelihood, and then we could also say, okay, like why do we do Bayes? I mean, Bayes kind of seems like difficult and expensive. We could also do maximum likelihood estimation. And it's like a much easier thing to do, like a classical frequentist thing to do. And you could do that. And what you would end up doing is you would just minimize this like squared norm in here, this like squared misfit. And that is a valid thing to do in some inverse problems. You can absolutely do that. And then you kind of get closer to this like regularized problem that we discussed earlier. We get even more closer to that a bit later today. But it's absolutely possible. One thing that is like just like a statistical thing that I always like to mention is, so I do call f, I always call f a parameter, but obviously f can be in the function space. And in statistics, parameters are only things that kind of live in like RD or like R to the n. So then statisticians would call this probably like non-parametric if the unknown thing lives in a function space. But I kind of like the word parameter, so I kind of still call it parameter, although the problem technically is non-parametric. It's just a notational thing. And then, so here we sort of assume that the data space is finite dimensional. You can also assume the data space to be infinite dimensional. And in inverse problems, that's kind of usually, especially in like imaging or so, people often work with infinite dimensional data spaces. In that case, you can't really write down its density because there is no density of this form for Gaussians. So you would need to use a Cameron-Martin theorem to find density. The density looks a bit different then. It doesn't look kind of completely different. It looks still very similar. But it's also a bit more difficult because you always need to make sure that you end up in the right space. So it is a bit more challenging, unfortunately, to work in infinite dimensions on the data space in this setting. Yeah, so this really is only finite dimensional data. Okay, you happy with this likelihood, more or less? Yeah? Is it your favorite likelihood for now? I mean, certainly it's mine. Okay.
Maybe just one thought,
Yeah.
because you described this as being a distribution, a Gaussian in G.
Mm-hmm. Yeah. No, it's in.
Or I always think. I think of it at least as a distribution in F parameterized by G, but then it's not like Gaussian in F. It's a Gaussian in A of F, right?
So I think this is wrong. So this should be L of G given F actually. That is just, did I do this incorrectly here as well? No, here that's right. No, so the likelihood is a distribution in G. Because the likelihood is a distribution of the data given the parameter. Mm-hmm. Yeah, so that has to be density in G. This is just a typo here. So this should be L of G given F. And then you have a Gaussian distribution in G. Because G is essentially a Gaussian sample with a known mean, if you know what F is.
Yeah.
So it just comes from the noise. The noise determines what the likelihood is.
Yeah.
Can I ask one question?
Yes.
What happens if we don't know the distribution of the noise?
Oh yeah, that makes it a lot more difficult. So what you can do is you can just add these as parameters. Yeah. So if you say that, for instance, you may not know what the variance is or so. Mm-hmm. Yeah. Then you could technically say it's like, okay, so just what is a gamma here? It's just another parameter that you want to estimate as well. It makes the estimation very difficult, though. We come back to that a bit later, I think tomorrow, if you're still here tomorrow. Because obviously, in a Bayesian setting, you often assume that you know everything. Yeah, so you know exactly how to choose all the parameters. But in practice, you often don't. And then what people often like to do are sort of like mixed strategies that are like partially Bayesian, partially not. And use the non-Bayesian strategies to kind of find hyperparameters or so. Because this weight, it's so important because what this noise is will determine like how much you trust the data, and then it determines a lot kind of like how big the variance is in the end of your posterior. Yeah, because if you say it's like, okay, the noise is really large, and then it's like, okay, it should be quite wide because you essentially have like learned very little, or you're really sure that doesn't make a huge difference. So it is kind of important to figure this out, what the noise is, but you could just add it as a parameter and estimate it as well, but it's tough.
Yeah.
Okay. So, we now know likelihoods, so we can now write down Bayes' theorem. And the important bit is actually this part here. So there are some assumptions, so we have a Frey density for measuring mu x, and we assume the likelihood is actually integrable with respect to the prior. Yeah, so you can actually write down an integral, which is usually the case because all likelihood is actually bounded above by 1 or so, or something like a Gaussian density is bounded above. Yeah, so that's usually not a big deal, but it's good to mention. And here we kind of assume the likelihood is always positive, which it doesn't have to be, but fairly often it is. You can also get away with it not being positive everywhere, but at least like PG almost surely, so it should be positive kind of where the data has mass. And most likely models do satisfy this, and if you kind of have one that doesn't satisfy it, if you have like a uniform noise model or so, which technically you could have, then you can always like reduce the size of your data space as well to account for that. Yeah, so data space doesn't have to be all of R to the D. So usually this usually figures out. And then we have this integral here, so like z of g is strictly positive. Okay, so we just integrate a positive function that is integrable, so that will be positive. We have that the posterior, mu post, also has a density with respect to this reference measure, which is given as the product of the likelihood times the prior. density divided by this thing called Z, Z here. Okay, so kind of very often we kind of like don't write this and just kind of just say like a proportionality sign here because the Z is just a constant that just makes sure that everything is a density. Yeah, so you just normalize it. The Z also has a meaning. Yeah, so it's a model evidence or so it's often called. And you can use it for certain things. It's not so important here. Yeah, but that's essentially basis theorem. Proving this is not so hard actually. So first of all, okay, I said this already, so it is positive everywhere, so that's certainly fine. And then what we just do essentially is we kind of just give the elementary definition for the posterior distribution. Yeah, so just as we had it before. Yeah, so just this ratio. And then we can do the same for the likelihood. Yeah, so then we see the likelihood is kind of the same thing, just with different parameter and with a different normalization. And then we just like do a bit of algebra. Yeah, we just like rearrange this. Yeah, so rather than doing a sketchable proof, I could have also have done just a proof because it's quite easy. Yeah, it's just like trying to match this term with that term, and then you're essentially done. Yeah, and then you see the basis theorem is true. And this is kind of the version that kind of works on a lot of different function spaces. Yeah, so this kind of is very. I mean, as I said before, you need only the space like radon or something. Yeah, so you don't need much for the space to work on, and the proof is just identical. Like since we've done all of the pre-work this morning, yeah, the proof is identical to a proof that would just be for Riemann integrals. But this just works everywhere essentially. Yeah, so that's something fun. Okay. Maybe just as a bit of a funny historical thing. So first of all, kind of, so like Bayesian was, I mean, he was not a mathematician, or not really. I mean, or not a statistician. He was a priest. And I mean, he was a fellow of the Royal Society, yeah, so he was sort of well regarded for what he did, kind of probably aside from, so that's kind of a big thing. Being a fellow of the Royal Society is a big thing. But kind of his paper on Bayesian statistics, that obviously didn't call Bayesian statistics, but he called like reasonable explanation something. I forgot how the paper title is, but it's a good paper, I recommend it. But it was only published after he died. It was published by someone else, like it was just a letter explaining things, and it didn't contain Bayes' theorem at all. Yeah. It did contain what I cited earlier today. This like definition of reasonable expectation. Yeah, so saying like, okay, the thing with you get £1 if you win the game. Yeah, so he did that. But he didn't come up with like Bayes' theorem. Who did write down Bayes' theorem is actually Laplace. So 1812. Yeah, so in this case, like the little p here is the prior, and h is the likelihood. P la probabilité a priori. Yeah, so that's the prior. Yeah, that's correct. And then h is the likelihood, and then here you get this normalizing constant. Yeah, so s is the integral or the sum. I guess it's a sum. My French is not that good, but it took me a long time to find it in the book. So that's the 1812. The book is called like La théorie analytique de la probabilité. So like analytical theory of probability. So that was like 120 years before Kolmogorov, who then turned probability into a mathematical subject actually. So this was very early. But he knew this already, and I think he's never read Bayes' work. I think they didn't really overlap. But I forgot when Bayes lived. I think a bit earlier maybe. Yeah, but. Yeah. So, but you can find it in Laplace's work, and can be happy about it. Yes. Okay. Oh yes. Okay. And here, right, like it's like maybe Bayes. So Bayes was not a super famous person, and I think this picture first appeared in a book like at least a century after he died. So it's pretty obvious that it's not him, but it's the only picture we have, and so we like to keep it. And if you are like a member of the International Society for Bayesian Analysis, you can like donate for the so they like look after Bayes' grave. So Bayes has a grave somewhere in the UK, and they look after it, and then you can donate like for the people who look after it, and you can donate for which I think is cool. It's nice that the society looks after that. They have a nice annual meeting as well. Yeah. Okay. Anyway, I'm just like too many tangents. Okay, now what is a Bayesian inverse problem? Because when we talk about ill-posedness, we kind of first need to fix what it actually means. And I fixed it some time ago because somebody had to do it. And so I say Bayesian inverse problem is we have a likelihood and we have a prior. And the Bayesian inverse problem is finding the posterior that has essentially this density given by a Bayes formula. Okay, and this is now just defined for, okay, we just have a prior, we have likelihoods, and now the Bayesian inverse problem consists essentially in applying this formula. Yeah, it's not more than that. And now, since we now know what it is, we can now wonder whether it's well posed or not. Okay, and I will tell you in just a moment what it means that it's well posed. Okay, what I should maybe say is here we assume now that likelihood actually is a proper function. Yeah, so before it was kind of a density, that's what I mentioned earlier with like existence of things. But we kind of assume here that we can point evaluate it everywhere, because that's important to get an estimator. Actually, and usually that's fine. Okay, so let's talk about well-posedness. So first of all, kind of the question whether it's or when it is well posed has been. I didn't bring a cup of tea. Okay. The question whether it's well posed or not has been around for quite a while, or had been around for quite a while. So there's a lot of papers here. I didn't mention all of them, but I think probably it's like Stewart 2010 again who probably started this discussion. And tell you a bit more about the results. So this is Stewart and some of the results here. And kind of the highlight ones are papers that I was involved in. Especially this like 2020 one, so that's kind of results that I'll show you in just a moment. Yeah, so that's 2020 on the proposals based inverse problems. And then I was very fortunate because the paper was reprinted, so like an updated version, and it appeared 3 years later in Sign Review. So I was very lucky to have this happen. So actually, when you want to read one of these, I will probably read the slightly newer one because it has slightly less typos. And it has some more information as well. Yeah, it's easier to read maybe. Okay. So what does now well-posedness mean in this setting? And okay, so we said the problem consists in finding the posterior, kind of given by Bayes' theorem. And now we would say, okay, it is well-posed on a metric space of probability measures, and I'll give you an example in just a moment. But we have P as a space of probability measures, and D is a metric on that space. And we say it's well posed if the posterior exists in this space, if it is unique, and if it's actually stable. And stable just means it's continuous in this metric space. Okay, so for all as a function of G, it's a function of the data. Okay, so for all G and all positive epsilons, there is a delta such that the distance between the posterior at the data set G and the posterior data set G dash is less than epsilon for any G that is for any G dash that is close to G in this norm. Yeah, it's just classical continuity definition of metric spaces. Yeah, it's just weird here because we may not be so familiar with metrics on space of probability measures, but we will just see a few examples now. Yeah, so one example could be total variation, for instance. So total variation, distance of two measures, it's just, we look at both measures, we plug in all possible measurable events, and just compute the supremum over all of those. So that's total variation. And here, so the space P is just all probability distributions on X. We can also say we want to do the Hellinger distance. That's quite so Hellinger is quite popular. It looks a little bit strange because it looks a bit like an L2 distance, but there's kind of one square root too many. Because you kind of it's like the L2 distance of the square roots of the densities. Okay, and so here we say, okay, this is now on all probability distributions that have a prior density with respect to the prior. Okay, so they're absolutely continuous with respect to the prior, which posteriors are, so that's fine to look at that space. And then we just compute this L2 distance of the square root of the densities. Okay, or we can say, okay, we take this like Bokov distance, which is just a metric showing weak convergence. Okay, so weak convergence always it's like weak star convergence when you think of function spaces, but it's called weak convergence probability, which essentially means that for any bounded continuous function Q, the integral of expectation converges if the distributions converge. those are just a few examples. There's a few more you can make, but I think these are maybe the easiest. And then there's a theorem, so from, you can find in these papers, that kind of has 4 conditions. So first of all, L is strictly positive, L is integrable as a function of f, here that's what we had before. There is some integrable k that bounds L uniformly, and L is a continuous function as a function of the data. Okay, which usually we have as well, in which doesn't, maybe I could just show you, actually we have a slide with comments on all of these, so maybe I don't show you that now. And if these 4 are satisfied, then we get ill-posedness in all of these metrics I showed you in the previous slide. So probably total variation, total variation and Hellinger actually are, I think, fully equivalent, so that wouldn't make a difference, but that is quite strong. If you instead want like something weird like curvature divergence, curvature is weird because it's not symmetric, but you can still use it like as a semi-metric, that's still fine. Or you want to use Wasserstein, then you need some additional assumptions on the distributions. So, kind of for all of these assumptions, I mean, so I think that's usually fine. Because first of all, this is by definition a Borel distribution, so that's fine. And it's usually, positive is not so hard to justify, because you could just also reduce the size of your space if it's not. So usually that's okay. W2 we don't even need because actually implied by W is 3. So if there's a function L1 that upper bounds it, then it's already in L1. This should be a k, there's so many typos here. That's usually satisfied by just choosing a constant, because very often, like Gaussian densities or so, we know we can just upper bound them by a constant. There's very few densities that actually go to infinity somewhere, because they need to integrate to 1 in the end, so very often they're just bounded. And continuous, that kind of sounds harsh, but it's continuous in G, not in F. Okay, so the Gaussian example, like before, we got this Gaussian likelihood from before. So here, I mean, obviously, this like A could be really horrible. So A could be discontinuous, could be like maybe no point variations, also could be really, really bad. But we just need continuity in G. Okay, and that is already continuous here in G, because it's just exponential and some norm, so non-squared. So continuity in G is usually fine for most densities that I know. And so these are not particularly strict, I would say. And actually, so if we go to the setting that I just showed you, then this is already like all satisfied. So if you have Gaussian noise, then you're absolutely certainly well posed in your Bayesian inverse problem. Which is nice. So you're safe. In a large number of realistic problems, you're absolutely safe. Okay. There's some more discussion. So can we do this for infinite dimensional data spaces? That's not so easy. So that's a bit more difficult. So when you observe functions, within the Gaussian white noise or so in infinite dimensional spaces, then you get a more complicated likelihood, and then you may need boundedness assumptions on A, because just likelihood is not a nice like norm squared anymore. It looks a bit different. So that's annoying. But you still get continuity of the noise density function, so that's still fine. But okay, if you have other noise models, then you kind of need those two. You need continuity in Y and you need boundedness. But that's usually fine. What we get here is only continuity, which kind of you could argue is not very much. But you also ask for not very much. So if you kind of look at more the classical works, they usually try to prove more, so they prove like Lipschitz continuity or so, Hölder continuity, which is a lot more than continuity, so that's a lot more helpful if you know that this is the case. But so this is more like a feel-good result, that like, you certainly know it's going to be continuous. It might not be much more, but also the result doesn't ask for very much. So it's a weaker result than what other people showed, but also under much weaker assumptions. And so if you know like a lot about the operator A, then you kind of may want to ignore this work entirely and just look at what like Stuart has done. But if you don't, so if you know, okay, it's a super difficult PDE, or maybe it's like hidden in software or so, or you don't really know what is going on, then this can be like the best thing you can get. And then this is actually nice. And then, just because it's well-posed doesn't mean that you should necessarily do it, because obviously you could have a very silly prior choice or so, and there may not be a reason for why this is a good model in the end that represents your uncertainty or so. So well-posedness is only like a safety net where you can say, okay, at least don't try to compute something that like doesn't exist, or I don't try to compute something that will be really unstable and that will have no chance of getting a sensible answer. But there are like many like statistical questions or so that you can ask. Like, so what happens if the noise disappears, for instance? Do you find the actual F? So do you converge to a Dirac in the actual F if there's no noise, if there's more data? Even better, do you get a Benjamin Mises? So it's a posterior approximately Gaussian around the true parameter, which is something we would often want to see. And this is all not included in the well-posedness statement. So well-posedness just means it won't blow up. It won't be completely mad, the result. But actually showing these things like statistical consistency also is quite important as well. And that's a lot more difficult. There's a nice book by Richard Nickel I can recommend. It is a bit of a tough read, but if you're interested in like non-parametric statistics, then that's actually quite, I would recommend it, yes.
So could I ask you, when you talk about infinite dimensional data, what do you have in mind as sort of an example? Because I mean, my data is something that's inherently discrete typically.
So obviously, okay. I mean, there's always the question, sort of, what do you expect to see? But what people do is like statistical or stochastic processes or so, where they say, okay, they get like a data point at a really, really high rate, and then okay, it's still like discrete, but it may be more sensible to analyze it as a continuous object, where you say actually, okay, this noise is technically discrete, but it very much behaves like actual white noise. So it's like for the deconvolution model in the beginning, where you say, okay, actually this is discrete. So actually the inverse will be continuous because it's a matrix. But when you look at the function space, then you actually see it's like, okay, this inverse will be so awful because on a function space level it is actually discontinuous. And then there are some things you really only see in the continuous framework. I mean, I think it's funny because I think when you go more to the say numerical analysis engineering community, then they always assume to have final amount of data. So they don't care about this whatsoever. If you go to the Austrian School of Inverse Problems, to like Christian Predis so they very much work from mapping from one function space to another function space usually. And I think I highlight this result here because okay, it's also in that paper, but also because there are like a few more imaging type things in this talk, and therefore I kind of highlight this because people quite like to work in. People that work in this framework for inverse problems, variational inverse problems, they quite like to work with infinite dimensional data. Although it may not be practically directly relevant. Okay. All right, are you now fans of Bayesian inverse problems because they're well posed? Yeah, best thing ever. Okay. Okay, I will just tell you a bit about Bayesian point estimators, and then we call it a day. Okay, so obviously now we know how to get this posterior density, and tomorrow we will learn how to approximate it, and then we will be absolutely excited and amazed by it. But sometimes people say actually it would be nice to actually just like look at an image and be happy with it. And maybe kind of getting a high-dimensional distribution is not that helpful after all. And the question is kind of what do we do then? And there's sort of two main ideas that we can use to find a point estimate. So literally like a point in X that gives us like a very likely output or like a very likely reconstruction parameter. One is posterior mean, the other one is a maximum a posteriori estimator. And we'll just talk about that a bit now. Okay, obviously the posterior mean will just be the mean of the posterior. Okay, so if we know the posterior, then we just compute the integral over f with respect to the posterior, or just the expectation of the posterior, or whatever to call this, and then we get this object. It's often called Bayes estimator. So it's the usual name for it in the literature. It does have some interesting properties. So for instance, it is the optimal L2 function to describe the mapping from G to F. Okay, so when we say, okay, we have our parameter and our data, we want to know which function in L2, mapping from the data to the parameter, is the best function at representing this map from G to F. That is the Bayes estimator. Okay, so that's kind of pretty exciting. It's not so difficult to see when you kind of think back of the Markov kernel that we didn't like, because there you kind of see that it's a bit like a projection, getting this Markov kernel, and then you can write the whole thing again without a Markov kernel, but for the conditional mean, and then you actually see, okay, this is exactly a projection, and then this is just kind of the rewrite of the projection as an optimization problem. Yeah, so that's kind of how you get there. It's not so hard to prove. Also on real space, not so hard to prove. Yeah, but this actually minimizes. So overall, L2 functions, this is the best one at mapping from G to F. Yeah, which is yes.
No, it looked like something similar to optimal transport somehow. So just look at it, it reminds me this, I don't know, when you want to minimize the Wasserstein distance between two density functions in L2, you should get, so the L2 version of the Wasserstein distance looks similar to this.
Yeah, I mean, it looks a bit like optimal transport, but it's kind of more like the other definition, though. It's more like the optimal transport definition, where you kind of try to actually find a transport plan. Yeah, so then K would be the T. That's often called T, because in like Wasserstein, you kind of try to find a coupling between two things, between two distributions, and here you actually try to find a function that maps from one to the other. So that's like a stronger thing. So I always forget how they're called because I'm not an optimal transport expert. But it's certainly true. That's certainly true. In some optimal transport definitions,
you can map. So you can place the optimal transport in several ways. One is this coupling that you say, but also like the optimal map that leads you from
one thing to the other.
Yes.
Yeah, that's kind of. But that is like I think it's exactly less flexible because it more often doesn't exist in certain cases. While the coupling you can always do. Yes, but you're right. Yes, it does look a lot like that actually. Yeah, you're completely right. Yeah, I never thought about that. Yeah, I should have thought about it. Yeah, no, it's a good.
I mean, if you have time.
Yeah, we can talk about this. Yeah, of course. What is also nice is if you have Hellinger ill-posedness, so there's like weird like square root of densities L2 distance, that actually we know that the Bayes estimator is also well posed. So the sense of that it's also stable, and actually with the same modulus of continuity. So that's could ask, okay, why do we use this like with Hellinger distance? But what it actually does is when you compute expectations in the two distributions, and you compare the expectation, then they scale exactly as the Hellinger distance does. Okay, so if you knew Lipschitz continuity in Hellinger distance, then you would also know automatically that this is also Lipschitz continuous as a function of the data, which is kind of a cool result. So that's why Hellinger is popular. What is a bit annoying is, I mean, kind of how do you approximate this Bayes estimator? And I mean, usually you first approximate the posterior, and then you take the posterior to compute the integral, which is not fast. And I don't think there's like a perfect way to get it otherwise. The other thing is it can have like a smoothing effect that is a bit awkward as well. Because so if you think about it, so if you say, okay, you have like an image and a picture. So maybe say we have like a binary image with like some object in the center here, and kind of this edge here is what we actually try to reconstruct, because it might be quite blurry, but the edge is uncertain, and so if we then compute posterior samples, they will all have a slightly different edge, because the edge is uncertain. And if you compute the mean over those, we will just get the blurred out edge again. So it's not so clear that this actually is the right thing in like deconvolution also. Because the mean might just be as blurry as the original picture. So which is in a way it's actually good. Because it tells you that okay, this is where the uncertainty is. So that's like a nice thing to know. But if my grandfather sends me a family picture to reconstruct, and it's like just as blurry as afterwards, I tell him, oh, but we know there's a lot of uncertainty. And it's like, yeah, okay, but it doesn't look nice. So I'm not gonna win. I'm not gonna win in that situation. And so that's why for some problems, the posterior mean is just not a really helpful thing to look at because it's expensive and because it might actually not give you the thing that you want to look. The maximum posterior estimator is a bit more like the maximum likelihood, but including the prior. Because now we say we don't just maximize the likelihood, but we actually maximize the density of the posterior, which looks a bit like this. So, okay, typically when we maximize the likelihood, we typically minimize, actually like minus the logarithm of it, which is fine, which is a lot easier. And then what we get here is like minus the log likelihood, minus the log prior, and plus the log model evidence. The model evidence doesn't depend on f, so we can just ignore that in optimization, which is great because we can't compute that usually. So it's good that we can ignore that. And then what we have is minimizing the data misfit minus the log prior, which is a bit like a regularizer. Okay, so we're actually back to the beginning of this morning. Where we said, okay, we have a misfit and we have a regularizer, and that is exactly like the Bayesian formulation of that what we've seen this morning. It's actually like a bit more difficult to see this because in like finite dimensions then we can just do this and it's all very obvious. So kind of here, kind of very cheekily said that like x is equal to r to the n. In infinite dimensions, it's not so clear how to do that because we don't have this density that may make sense. We may have a density, but as respect to like a prior, like say like Gaussian prior or so, and that might be quite a weird object that then doesn't really contain information of the prior. Okay, so this density could be something slightly weird, and then we don't really know how to do this. There are like other ways to define a map estimator in infinite dimensions. But it does take a lot more work. And then you still get something that looks, in the end, you will still get something like this. You will still get something that you know from before. So everything is okay. But just the idea of what is the maximum of a density in infinite dimensions is kind of a difficult concept. I'm not an expert on this. There's nice papers. If you want to read some, I can send you something. But you can, for instance, look at this paper by Helen and Burger. But actually, kind of what is a map? Or what is the maximum of a distribution? It's not so easily defined. So just this as a disclaimer. Now, when this is a good idea, we get it just for optimization. So we don't need to worry about approximating the posterior at all. We just optimize. It's like variationally inverse problem. So we have algorithms for these. We can just optimize and we're finished. And then for some things, the properties seem to be better. So when I just want, like when my grandfather wants a nice reconstructed picture and doesn't care about the uncertainty, then this might just give him a nice picture in the end. Because there we understand quite well the thing that I mentioned earlier is like, okay, the prior forces us to be in the right function space, and then we will get a good reconstruction afterwards. The thing is, we don't get the well-posedness automatically from Bayes. Okay, so we need to work a bit harder to see that it's well-posed. Because actually, I mean, it is kind of a Bayesian thing, but then again, it's like the least Bayesian of them all somehow because it's quite far away from typical Bayes. Okay, so just as an outlook, okay, I'll not do the recap, but just as an outlook is, so we now kind of know how we get its density, how we get the density. Maybe we don't really know 100% because unfortunately to get the density we need to compute this integral z, and we can't compute the integral z in practice because it's too high dimensional and it's a tiny value usually, so we can't do this. So while we have a formula for the density, we don't really have it. and we rather want to approximate it somehow. And we will do this with samples. That's something we talk about tomorrow. And then the question is kind of what is a good prior distribution, which we don't really know yet, especially on function spaces. That's kind of a difficult question. And then are there some properties of posteriors that we find interesting? Okay, kind of we've done this today actually, sort of. So I don't think there's more on that tomorrow. I'm not sure. This list of outlooks is a bit weird. All right. Thank you very much.